Trust is the foundation of any system where multiple parties interact. In centralized networks, trust is enforced by a governing authority. However, in decentralized systems, ensuring trust without a central authority is a fundamental challenge. This is where the Byzantine Generals Problem comes into play, a theoretical problem in distributed computing that directly relates to the way blockchain networks, such as Bitcoin, achieve consensus and prevent malicious actors from disrupting the system. The Byzantine Generals Problem is a thought experiment that illustrates the difficulties of reaching agreement in a distributed network where some participants might be dishonest. Imagine a group of Byzantine generals planning an attack on a city. They are spread out in different locations and must coordinate their attack by sending messages to one another. The challenge is that some of the generals, or their messengers, might be traitors, sending misleading information to cause failure. The problem is as follows: how can the loyal generals ensure that they reach a consensus on whether to attack or retreat, even if some of their messages are false? For a successful strategy, they need a protocol that allows the majority of generals to agree on the same decision, regardless of misinformation from traitors. In the context of computer science, this translates to the challenge of ensuring that a distributed system can function correctly even when some nodes, participants, act maliciously or fail to communicate reliably. Blockchain networks, such as Bitcoin, are decentralized, meaning no single authority dictates the validity of transactions. Instead, consensus must be achieved across numerous nodes that do not inherently trust each other. The issue is that some participants could act dishonestly by attempting double-spending attacks, falsifying transactions, or disrupting the network. Bitcoin's creator, Satoshi Nakamoto, designed a solution using proof-of-work (POW), a consensus mechanism that ensures all honest participants can agree on a single version of the blockchain, despite the potential presence of malicious actors. POW effectively mitigates the Byzantine Generals Problem by making it extremely costly for attackers to manipulate the system. Bitcoin's POW mechanism relies on a process called mining, where participants, miners, compete to solve complex mathematical puzzles. The first miner to solve the puzzle gets the right to add a new block of transactions to the blockchain and is rewarded with newly minted bitcoins. This system addresses the Byzantine Generals Problem in the following ways. In order to propose a valid block, miners must expend computational power. This ensures that any attempt to deceive the network requires an immense amount of energy and computing resources, making dishonest behavior economically unfeasible. Bitcoin follows a simple rule: the longest, or most computationally difficult, chain is considered the valid one. This means that as long as the majority of miners are honest, the truthful chain will always outpace any malicious forks. Miners are rewarded in bitcoins for their work. If they attempt to cheat, they risk losing their rewards and investments in mining hardware and electricity. This financial incentive ensures that rational miners follow the protocol rather than trying to attack it. The more participants in the network, the harder it is for a single entity to control more than 50% of the mining power, which would allow it to rewrite transactions. This is why a widely distributed network is crucial for Bitcoin security. While POW is the most well-known solution, other consensus mechanisms also tackle the Byzantine Generals Problem in different ways. Proof of stake, POS. Instead of computational power, validators stake their own coins to secure the network. If they act dishonestly, they lose their stake, ensuring economic alignment with network security. Delegated proof of stake, DPS. A selected group of validators reaches consensus, making the process more efficient but slightly more centralized. Practical Byzantine fault tolerance, PBFT, used in private blockchains, where a fixed set of nodes reach agreement through voting. Each approach has trade-offs between security, decentralization, and efficiency, but all aim to solve the same fundamental issue, ensuring consensus despite potential adversaries. The Byzantine Generals Problem highlights the difficulties of achieving consensus in a system where trust is not guaranteed. Blockchain technology, particularly Bitcoin's proof-of-work mechanism, provides an ingenious way to ensure trustless consensus in a decentralized network. By making dishonest behavior prohibitively expensive and rewarding honest participation, Bitcoin and other cryptocurrencies have successfully addressed this long-standing problem, paving the way for decentralized and trustless financial systems. As blockchain technology evolves, newer consensus mechanisms will continue refining solutions to the Byzantine Generals Problem, making decentralized networks more secure, scalable, and efficient than ever before.